Since we're at the halfway point of the program right now, I thought I should give a talk that covers everything of past and future. No, I'm giving a talk that will basically touch on everything in the program, except not so much really on operads, but they're there.
They're always there.
They're there. And bar construction and other things. So what I'm going to do is actually I'm going to give this talk twice today. The first one will be short, maybe half an hour, and I will give a complete overview of everything I'm going to say. And then I will go back and do it again, and I can't possibly prove everything. There are 10 or 20 theorems. But at least for the main ones, I can give the flavor. I can really tell you how they're proved and what the ingredients are in the proof and what techniques were used to prove each one. So first of all, of these 5 things, the 6th one has become invisible, but that's probably good because I think I will truly never get time to get to the 6th one. Of the 5 that you can see there, these 5 Lie algebras, my heart is close to number 1, obviously. So okay, what I like about the Grothendieck-Teichmüller Lie algebra GRT, which I call Grot, I hope you don't mind, is that is connected to all these other objects which come from different parts of mathematics. Some of the connections we've already started to see. But there's something else that if I were to say GRT is connected to many other things in mathematics, I could give a whole different talk on that same subject. Because there are many people who work on GRT acts on, well, we saw that the group GT acts on fundamental groups of genus 0 moduli spaces, and the Lie algebra does the same thing on Lie-braid algebras. But it acts on many, many other things. Some of them are very foreign to me. We have people coming, Vilva, give a talk. They act on formality morphism, all kinds of things which are really very different from what's in this talk. So that would be a whole different aspect of how GRT keeps appearing in the wider world. What I want to do here is I want to take the objects that we've seen so far and some that we haven't seen yet, but that you will see next month, and actually show, well, we conjecture that here are 5 Lie algebras. I'm going to give you all the definitions. My talk is going to be like this, all the definitions at the beginning, on slides. So I can leave something there for a while I'm talking to you. And then no more definitions. I'm going to define the 5 Lie algebras. And we conjecture that they're all isomorphic. So this is really the overview, or the picture of the talk I'm going to give today. What are these 5 Lie algebras? Where do they all come from? Why do we conjecture that they're all isomorphic? How similar are they? What do we know about their similarities? And what maps do we already have between them? Some of them being already isomorphic, and some of them being at least injecting into others, okay? So these are the 5. And the first one, you've seen it already. I'm going to go through the definitions completely before starting with any of the results. So we saw this one. So I'll go a little more quickly over the first couple that we've seen already. We have the braid Lie algebra. We saw it already in my talk 2 weeks ago and in Damien's talk yesterday. The braid Lie algebra is the Lie algebra associated to the 5-strand braid group. And you need to introduce that in order to define the Grothendieck-Teichmüller Lie algebra. Grothendieck-Teichmüller Lie algebra is just made of Lie polynomials, just Lie polynomials, so brackets of x and y's together. The elements of GRT are just polynomials that are brackets of x and y's. So you can they're graded, and you can calculate the first ones very easily. So it's really something that you can work with explicitly. Sort of explicitly, because in truth it's not that easy to literally work in the braid Lie algebra and check the pentagon relations.
Mike, it's not on.
Oh, it's not on. Oh, I have such a loud voice. Make a difference. Okay, I'll be even louder now. Okay. And people did explicitly work on the pentagon. You have some way of calculating the braid Lie algebra. You have to have a basis. And you can find GRT. Lie polynomials explicitly up to some high degree like 20. Okay, so thanks to a theorem that we saw 2 weeks ago due to Furusho, it turns out you don't need 1 and 2 in this definition because they're both implied by 3. And I think it's very important to say that this theorem, which works in the Lie algebra, okay, it also goes through to exponential of the Lie algebra, so to the unipotent group associated to the Lie algebra. Now, we saw this unipotent group yesterday when Damien defined the Drinfeld associators. They're series, they're power series in x and y, power series in two variables, and they define, and they satisfy three relations. And the second relation, it looked like this. I won't write it all out, or maybe I will write it all out. So x, I guess, this one. So it's xy, zx, yz. These are just all power series in x and y, nothing complicated. And when you take the exponential, the Lie exponential for the pre-Lie law of the Lie algebra GRT, you get such a power series, and it satisfies this except without these. So it satisfies the pentagon that he wrote yesterday, the same pentagon. So it's almost an associator. It's an associator. It's a Drinfeld associator, but without these terms. And so what I wanted to say was, what the theorem that Foucault proves in this context is that if you have a phi which satisfies the, I won't write it all out, but the pentagon, if phi satisfies the pentagon and degree 2 of phi is 0, because everything coming from GRT, when you take the exponential, it won't have any degree 2 part, because by definition, it starts in degree 3. Then, you get this for free. This is a consequence of the theorem that he proved. So you don't need to write this down. You get, so this was relation 2, and relation 1 was just phi xy equals phi yx equals 1. You get 1 for free as well. So if you have the pentagon, in the group situation without these terms, you don't need the other term. I'm not sure how true the theorem is for Drinfeld associators in general. Do you know? For Drinfeld associators in general, if you have pentagon, and can you get back?
Drinfeld associator will have degree 2, right?
Yeah, in a general Drinfeld associator, you'll have the pentagon, but you'll have a degree 2 part. But you can still prove 2 and 1?
Yes.
Yes, so it's always true. What I said here are those that you get without degree 2 part. They all come from exponential of GRT. But if you take one that has outside pentagon and does have a degree 2 part, then you still get 2 and 1 from the pentagon. So that's a very, very nice theorem if you want to calculate anything, because you don't have to check 3 relations, but only 1. Okay, so those are Drinfeld associators, call them associators. The elements of GRT, I call them Lie associators. And the thing to keep in mind is that you only need the pentagon. A Lie associator is a Lie element in Lie of x and y that satisfies the pentagon, and that's it. So we used to have 3 associated relations, but now we only need 1. So pentagon, associator, same thing. Okay. Now, main result about GRT, defining, part of the definition really, is why is it a Lie algebra? So I already did this 2 weeks ago, so I'll just go over this quickly. Every element of Lie of xy yields a derivation of Lie of xy, just by it maps x to 0 and it maps y to y bracket itself. And then you extend to a derivation, and just bracketing the derivations and writing down what that does to the polynomials, it gives you a very explicit form for a new Lie bracket on the same vector space. So you take your vector space Lie of xy, forget the ordinary Lie bracket, take this vector space Lie of xy and put a new bracket on it, which is the Poisson bracket. It comes from bracketing derivations. So you can see that GRT is this way. You can include it into derivations of Lie of xy. And oh, thank you. I can beat people now, that's good.
No.
Anybody bad? Okay, so Ihara proved this was quite a long time ago. Ihara looked at GRT a long time ago, in the 1990s. I think in the late 1980s even. He was already studying this Lie algebra. And so he showed that it's closed under this Poisson bracket, that it actually forms a sub-Lie algebra. So GRT is a Lie algebra for this bracket. Think of bracketing derivations. Now I'm just going to associate a different derivation here with a tilde on it. Just an x to f of zx and y to f of zy. It's completely equivalent. It's just I've just permuted x, y, and z. This is a completely equivalent definition to the one above with just a change of letters. But this one is actually better to go with all the other things we're going to say about other Lie algebras.
And if you stupidly consider the bracket of the free Lie algebra, GRT is not a Lie algebra. You need to place like this.
No. If you normal bracket two things in GRT, they go away.
This is too nice.
Yeah, well, it's hard to keep the pentagon. Okay, so that's all I'm going to say about GRT, right? In the first part of this talk, I'm going to sweep through the definitions and just the really main properties of the 5 Lie algebras. When I say really main property, I mean why is it a Lie algebra? I'm not going to go into things like it acts on something and relations between them yet. So I'm moving on to the second one right away. So we saw a lot about this yesterday. Okay, so original Cauchy-Weierverne problem, characterize pairs of Lie series that satisfy that relationship. Okay, he gave several different forms of the problem, actually. He gave, I think, 5 or 6 different reformulations, and this might be yet another one, number 7. But it's equivalent to what he was saying yesterday. This B is lower down on the slide. So CH is just kind of a Hausdorff law. G is the thing that Damien defined yesterday. The div, so you could take any polynomial in the non-commutative variables and write it this way. You just crowd together all the terms ending in x and all the terms ending in y. And this is a definition of the div. Let me talk for a second about the trace. This is a very interesting thing. To define the second condition of Cauchy-Weierverne, you have to work in the trace quotient of non-commutative polynomials. So you have Q of xy, non-commutative polynomials, and the map that Damien defined yesterday, I'm just going to say what it is in a really, really simple way. So a word, x, very often I'm going to write my words like this. I'm going to consider the powers of x between the y's. Of course, the powers of x can be 0, and you can have powers of y, obviously. But this is a convenient way to write the words.
Why do you have
X to
an
0. The last letter.
AR.
X.
But it's X, no, it's X.
Okay. Okay. So this goes to the equivalence class of cyclic permutations on the letters of W. So you would map, for instance, x, xy, xy would map down to the whole equivalence class of itself, this is really just the trace map that he defined yesterday. Now, they don't all have the right number of things in the equivalence class because words can be symmetric. So if, for instance, if you take this one, it's got a very small equivalence class. And this, it's a bit of a drag when you want to count things, but you have to take into account the size of the equivalence classes. So this is the trace map. So what are you doing when you're taking the trace? So you can see that axx plus ay plus byy is just a polynomial, just a polynomial x and y. What do you do when you actually calculate the trace? You calculate the coefficient of each of these words in your polynomial and add them up. And that's the coefficient of your equivalence class. Okay, so what is the trace of, this is the expression that keeps coming up in Cauchy-Weierverne. Well, before I write it, let me go to the linear version before I start writing. So here is the problem that you look at if you want to work in Lie algebras. So yesterday, in one of the many reformulations, Damien wrote down that the first condition on the F's that's a solution of the KV problem is this. And this what I've written up there, the first property of the solutions to the linearized KP problem is just the linearization of this. So conjugating e to the x is like bracketing x in the Lie algebra situation. And conjugating y to the x is like bracketing y. And this is nothing. And in the second one, div AB is just what we just saw. Div AB. Again, Damien wrote an expression just like this yesterday. Okay, Damien wrote this. X dxa plus y dyb. So, okay. You're going to use dx for a completely different derivative. So I don't want to use that notation. I just prefer to write ax x. But this is what he was calling dx of a. Well, it's x is on the other side. But in the trace you don't care whether x is on the right or the left, right? Because it's cyclic permutations anyway. So this is what the div AB is. And what is the trace of... Okay, when you're working in the Lie algebra situation, you can assume everything's additive. All these definitions, so you can assume your polynomial is homogeneous of degree n. So that means that you have a one-variable polynomial which is homogeneous of degree n. And so it's just x to the n. So that's very agreeable. You just have this polynomial. Okay? So this is very easy to calculate the trace of this polynomial. I mean, when you look at this polynomial in the non-commutative algebra, it's got one of each monomial, exactly. Except that x to the n and y to the n. And then you just have to, some of them have smaller equivalence classes than others, and there are some well-known coefficients that you have to count up. Okay. So, the basic technique for comparing all of the Lie algebras that I'm talking about is going to be to put them all inside the derivations of Lie of xy. So we already saw GRT maps to derivations of Lie of xy, and we're going to do the same thing here. And this is how they're all going to become identified. So for pair AB that solves the problem, you just make a derivation. X goes to xa, y goes to yb. So you make a derivation. And that's kind of obvious. But what's not obvious is that the bracket of derivations makes this into a Lie subalgebra. Again, so that's the theorem, one of the theorems of acceptation, is that if you bracket two of these derivations, they are going to satisfy the properties 1 and 2 again. So we're again working with a sub-Lie algebra. Now, algebra number 3. Okay, 2 weeks ago I already defined this Lie algebra, and I talked a lot about multiple zeta values. So right now I'm just going to give the most economical possible definition of the Lie algebra, and all the discussion about multiple zeta values and the role they play here will be later on in the talk. Right now I'm going to just give the definition of this, again, as a subalgebra of der Lie xy. Okay, so first we're going to use that notation yi is x to the I minus 1y. So any word in x and y that ends in y, you can rewrite it as a word in these yi's. I'm just going to look at you in my whole talk, okay? So when you say sure, I know it's okay. Okay.
If I do not understand, I will ask the question.
Yeah. Okay. I take an f, I take a Lie polynomial. I can always assume everything's homogeneous in degree n, which is the wonderful thing about Lie algebras, because you can actually calculate everything. And I let pi y of f just mean forget the words ending in x, just keep the words ending in y. Just ignore the other ones, keep the words ending in y. Then I can rewrite the whole thing in those yi's. So I do. I rewrite it in the yi's. And I add on a little correction term. This notation I always use for a coefficient. That's the coefficient of the word w in the polynomial f. Okay, so I look at the coefficient of that word, which can be 0, it can be any Lie polynomial, whatever. And I take that f twiddle. And I'm going to give 2 definitions of this. One is shorter and one is cuter, well, depending on your taste. So here's the definition. You take all Lie polynomials f of degree greater than or equal to 3, so we're in a good position to compare with GRT already. And you take, oh my goodness, I've left a tilde. I've left the tilde out of the slide. you're going to apply this coproduct to f tilde, and you want it to be primitive. F tilde is the one which is written in the yi's, not f. The defining condition instead should be with the tildes on all three places. And delta star is a coproduct defined on the yi's by this simple expression. So I can apply delta tilde to f, and I just check this condition. And that's the first and easiest definition of the double shuffle Lie algebra, but it's really not easy to prove that it's a Lie algebra under the same old bracket, which again, you associate. Well, you can do this just like, you can write the expression that we had. It's just the normal bracket of fg plus df of g minus gg of f. And it's really not easy to prove that it's closed under this bracket. And this was a theorem of Jussieu in his thesis. And there hasn't been any somehow easier way to understand or show this since he did that quite a few years ago. Now I'll just give a second definition of the double shuffle Lie algebra because it seems worse, but it's actually much better when you're going to be comparing it with the behavior of multiple zeta values, which are the dual object. So also we saw this 2 weeks ago. Okay, you have two sequences of strictly positive integers. One is called A and one should be called B, but seems to be called J, but should be called B. This is the bad thing about slides. Can't correct them. Okay, and you stuffle them together just by the recursive little methods that give it there. So first of all, the first line says that if you have a trivial, an empty sequence and a sequence, then the stuffle is the sequence. And the second one says, so the stuffle of two sequences I'm giving it to you is a set of other sequences. They're not all of the same length, some long, some short. And it's recursive. You take out the first character of the first and stuffle what remains. You take out the first character of the second and stuffle what remains. And then you add together the first of each and stuffle what remains. So it's just recursive. A couple of examples. Now, what I said last time, and I'll get back to it later today, is that this rule exactly comes from multiplying power series of the multi-zeta type. So I'll say it again later on when I get to more detail. It's not a weird rule. It's a really, really natural rule that comes from multiplying power series.
Stuffle of 2 and 3?
Yeah, 2, 3, 3, 2, and 5. Because I took out the A1 plus B1. There's a term where I take out A1, which is 2.
Two shuffles.
Yeah, I can write it. So it's 2 dot the stuffle of empty with 3, which is just 3. And it's
You remove and you remove.
and then it's 3 dot the stuffle of 2 with empty, and then it's 5 times the stuffle of empty with empty.
And 2 times.
So stuffle of empty with 3 is just 3, so it's just 2, 3.
And 2 times the string is you put 2 in front. That's the rule.
I didn't mean 2 times. I really meant comma.
Okay, yeah. Sorry.
It's 2 comma, and the stuffle of empty with 3 is just 3.
Sure.
Okay, so this is an equivalent definition of double shuffle, and the reason, well, it's a better definition if you want to compare with the dual behavior of multizetas, which we will later, and it's also a better definition if you want to understand the word double shuffle, because at least there's a shuffle relation here. So you take your Lie polynomial, f, and you, okay, is that a mistake in the slide again, which I'll tell you. You take two sequences, A and B, and you make the associated words in the obvious way, and you stuffle them together in every possible way. So stuffle of A and B is now a set of many sequences. And for each of those sequences, you make the associated word. And then you add up the coefficients of f in those words. And that is equal to 0, but I forgot this. This is kind of important. I mean, it's a little detail, but it's still, I should say it. That definition holds for all words, pairs of words, not both sequences of ones. So A can be a sequence of ones or B, but not both. Otherwise, it's not really wrong, but you have to add a little correction. Okay, so that's the definition of double shuffle, and the one thing to really keep in mind about double shuffle is that, okay, it has the same Lie bracket as GRT, and it's made of Lie polynomials, and it's dual to multiple zeta values. So this gives them the major aspect, the major reason for its existence, really. So I'll get back to that later. Number 4 now. Okay, we talked a lot about Galois Q bar over Q in all the profinite parts of our lectures, and its action on pi ones of G to 0 moduli spaces, which we're seeing as braid groups, so GQ acting on braid groups. So there is a Lie algebra version of that whole theory too. Obviously, when you go from an incredible group like Galois Q bar over Q to a Lie algebra, you're going to lose massive amounts of information, but that can be good because you can prove more. So, okay, I'll tell you something. Many, many years ago when I was really quite young, long time ago, I was very highbrow and I thought profinite groups are great and Lie algebras are stupid. And why would anybody work with a Lie algebra when you can work with Galois Q bar over Q? And I was learning this, so I was early on and reading Drinfeld's paper and getting into profinite. Even pro-unipotent seemed too low to me then. And I changed. But anyway, I listened to a talk by Ihara, and the amazing thing was he said the exact same thing. He said, I'll never forget this. It made such an impression on me. He said, profinite world, he really said this. Maybe you were there. Profinite world is like an eagle soaring in the sky, seeing great panorama down below. The Lie world is like a very low room, very low ceiling where you can't sit up. But you can see everything in this room. Everything, every little object, you can study it. And here, it's too far, and you can't. So I was very struck by this. I thought this is the exact, completely perfect right thing to say. It's true. And actually, I was struck by it at the time because I thought it was funny. But later, I was struck with it because it's so true. So now I love the little low room, and I live there. So I moved from the sky. Okay. So what happens with the Lie algebra is, how do you make Galois Q bar of Q? How do you associate a Lie algebra to this profinite group? What you do is, okay, well, it's written up there, so I don't have to write it. You take our favorite fundamental group of all time, which is the pi 1 of P1 minus 3 points. It's only our favorite because it's easy, obviously. But we do tend to spend a lot of time with it. And we know, because we saw at great length, that GQ acts on the profinite version of this group. Now, here is something which is very intriguing. To make the Lie algebra, you cannot do anything that I'm about to say without a prime number. You have to have a prime number. If you don't have a prime number, nothing I'm about to say works. So you're not making a Lie algebra over Q. When you do what I'm going to tell you, what you are going to get is a Lie algebra over QL for each L. And we now know that there is a Lie algebra over Q such that tensored with QL, it gives the Lie algebra that I'm about to define, but you can't seem to get it directly from GQ. So what Ihara did, way back when, Danini and Ihara, is they took the pro-L completion of that pi 1. So pro-L completion, it's just the inverse limit over all finite quotients, as always, but where this is an L group. So it's a quotient of the profinite completion. It's a miserable, little, nilpotent quotient. But you can work with it, which is the great thing. So you take the descending central sequence of that pro-L completion. And now, because when you go from the profinite group to the pro-L group, that's a quotient. You're just inverse limiting over less subgroups. So the profinite goes to the pro-L, and the kernel is characteristic. The kernel of this, it's going to be preserved by every possible automorphism. And so the action of GQ acts on this, and that will make a GQ action on this. And now you can go down again. You can map this to pi 1L mod its own central descending series, any of those groups. And again, because those groups are always the kernels are characteristic, the action will always pass here to an action on this as well. But this is injective, this is not at all injective, and this is even much less injective. And so you have kernels, and what Ihara did is to study the kernel. So he used those kernels in the descending tensor series to make a filtration on GQ. And now you have a theorem, which is striking, but it's not that hard to prove, which is that the successive, it's not on the screen, which is that the successive quotients are abelian. So once you have that, as soon as you have an abelian group, of course, you immediately add them up to make a graded vector space. And this graded vector space turns out to be a Lie algebra in a very simple way. Again, this is striking to say, but it's really not at all hard to actually prove. How do you make this into a Lie algebra? You take an element from any chunk and any other chunk, and you just lift them up to Galois, to the Galois group, any way you want, and take the commutator, and go down again. And the thing to prove is that it's well defined according to how you lift. And this turns out just not to be a problem. Commutators go away when you're acting on something mod commutators, basically is the idea. So that's actually quite an easy result. So the Lie bracket on this Lie algebra is basically just commutators of Galois elements. Okay, but again, okay, it's over ZL, but I tensor it with QL. But there doesn't seem any way to define this directly over Z or Q, even though we now know from theorems that I'm coming to later that there is a Q algebra, which is equal to this one when you tensor it with QL.
Excuse me, GQI is smaller than GQI minus 1. So, opposite. I minus 1 should be I plus 1.
I minus 1 should be I plus 1. I plus 1. Sorry, they get smaller and smaller, because the G0 is the whole thing. Sorry. How do these things happen? Okay. Okay, I'm going to my last one. Now, this one. Okay. Okay. First of all, there's going to be a course next month on this subject. So I'm not going to get into detail, because why should I give in a few minutes lectures which they will give in several hours. Nevertheless, I think it's not a bad thing to see it a bit now. And so what I'm going to do is I'm going to cheat and just give a really easy way to view this. Really easy, which of course leaves all the depths aside and hard work of everybody, okay? Due to many people's hard work and difficult definitions, we now know that the category of mixtape motives is equivalent to a category that's quite simple to describe. So I'm just going to tell you that. Okay, before I tell you what the category is, let me just, the Lie algebra that I'm going to be talking about is the free Lie algebra with one generator in every odd weight. Okay, just free. So you just bracket these SIs together. This is the Lie algebra that my fifth one of my collection, that all the others are supposed to be isomorphic to. Okay, U, XF is the associated pro-unipotent group. The F is graded if I let SI be of weight I. That gives a grading on F. A grading on F is like giving a GM action on F. And if I have a GM action on F, I can lift the GM action to U. That's just a detail. It basically means the Lie algebra is graded. And the category of mixtape motives is equivalent to the category of representations of that group, U, semi-direct GM. So what that does tell you is that a mixtape motive is equivalent to, or is often, is a finite dimensional. It can be infinite dimensional if you take a pro-ind object or something. So let's not say finite dimensional. Vector space with an action of that group. So, in a sense, that's all that a mixtape motive is. But of course, the rich thing about mixtape motives is where they come from, the ones that we actually study. What are they? How can you just get a vector space with an action of that group? And they come from geometry. They come from, well, essentially they come from pi1 of p1 minus 3 points, so Lie of xy. To prove that you can have an action of this group on Lie of xy viewed as a vector space is a very big and very deep result. It's this famous paper by Deline called, what is it called? P1 minus 3 points? Something P1 minus 3 points. And the whole paper, at the time, I guess the phraseology of understanding what a motive is was a bit different, and he was really thinking, at that time, a motive is a whole collection of realizations towards different categories. And it took a very thick and difficult paper to show why the pi1 of p1 minus 3 points is a motive. Okay, so the difficult thing is to give examples of these motives. And they come from geometry, they come from the moduli space, the genus zero moduli space, and essentially now the most important examples that we study are motivic multiple zeta values. So I have to talk about those quite a bit later on when I'm going to be proving things. But right now I'm not going to tell you anything about any actual motive. I'm just going to say motives are these vector spaces equipped with an action of this group. And when you have a Tannakian category, any Tannakian category of objects with tensor products and various axioms, any Tannakian category is equivalent to the category of representations of some group, always. And that group is called the fundamental group. Okay? And it's unipotent, or it has a unipotent radical. It's pro-algebraic with a unipotent radical, and the Lie algebra of the pro-unipotent radical is called the fundamental Lie algebra. So what I just said basically is equivalent to rep of a pro-algebraic G. U equals unipotent radical of G is called, this is really what we call it, the fundamental group of the categories. VU is called fundamental Lie of the category. So it is known that the fundamental Lie algebra of the category of mixed state motives is this F. And that result is due to Davidson, maybe? Davidson, I don't know exactly, using K-theory theorem by Borel, basically, in a fundamental way. Okay, so the last sentence is a bit lighthearted, but I have to say it. Lie of xy is the Lie algebra of the free group bunch of generators, which is the pi1 of p1 minus 3 points. And fundamentally, for this reason, Lie of xy is a mixed Tate motive, and it has an action of this group on it. So I just said something very deep in a very simple way, and I'm really not telling you anything explicit. And in fact, it's extremely hard to know anything explicit. At least it was before the theorems that I'm going to be talking about now, which are all very recent. And now we do have a way of calculating the explicit. We do and we don't. The word explicit is actually a very dangerous word, right? The word explicit is a dangerous word. Sometimes explicit means you can give a closed formula. Sometimes explicit means you can give an algorithm. Sometimes explicit means you can do it explicitly with a formula or an algorithm if you have a certain conjecture. So every time I say the word explicit, I'll be careful with this. At this point, I guess I have to say we cannot calculate the action of f on Lie xy explicitly. We cannot, unless we have some tool like a conjecture, at least, in which case then we can do everything explicitly. But okay, I think that the correct statement as of today is that we cannot do this explicitly. We just know it acts, because this is a mixed state motive, but we don't know how. Okay, I'm done. I'm done with my definitions, so there won't be any more definitions today, except the mixed state motives at some point. I will get there. Now I want just to give an outline of the whole rest of the talk. And this is basically what it is. So the main conjecture of everything here is that they are all isomorphic. The only annoying one is the Deligne-Hara, which can't be defined over Q. So you have to tensor everybody with QL to get the isomorphism with that one. They're all isomorphic. And underneath, well, this is where we are so far. And it's all very recent work. I've put down here. So F, I'll put this here because I have to take it off the screen so that you can see it. Okay, so that's progress to date. And now I'm going to talk about the end of the introductory part of my talk is that I'm actually going to try and prove all of these results for you in a few lines. Just because I think it's really important to give the gist of and how different these proofs are and where they come from and how they fit together. And then I'll go back to the beginning and give more detail on some of the parts. So, first, you saw this 2 weeks ago. The interesting thing about this injection here is to wonder how it was first even observed, because this one is the first of these many conjectures to even be made. And the motivation for the conjecture, I have to mention this now. I think this is a key moment to mention the Drinfeld associator. Okay, we talked a lot about Drinfeld associators yesterday, but there's one. It's the phi kz, the Knižnik-Zamolodchikov associator. This is the first main associator that was ever defined, and it's also one of the only associators that anyone's ever written down. We seem to have another one now, recent work. But basically, this was for a long time just the only Drinfeld associator that anybody had actually ever seen. And it's given by the sum of, over all words in x and y, zeta of w, where zeta of w is the multi-zeta. I will come back to the detailed definition later on, and I actually started it last week. So right now I'm just going to say it's the multi-zeta value if w starts with x and ends with 1. If. Then you can write it this way. So here's the idea. This is given by a convergent power series. You just associate it to a word in this way. You extend that definition to all words. I'll say more about that later. And you define this. And if you do this, and this is the fundamental theorem of Drinfeld from a long time ago. This power series satisfies the double shuffle relations. Well, I wrote them down in Lie double shuffle. So log of this satisfies the Lie double shuffle relations. And it satisfies the associated relations. It does both. So what I'm saying is there are objects in nature, these multi-zeta values, that satisfy associated relations and double shuffle relations. And this is the heart of the connection between those two objects. So I'm really talking about this part now. Now, when people wanted to compare the actual Lie algebras, well, that's quite easy to do in small way because you can calculate everything. I'll write down the first element for you so you know what it looks like. The weight 3 element in GRT is just x, xy, minus xy, y. The first weight 3 element in double shuffle is, well, this is the basis of the weight 3 part of the Lie algebra. So it's not surprising that you have the same terms, but the coefficients are very similar. And in fact, testing on computer showed that all you have is this. This is the map. And this is very, very surprising because it's the same polynomial. It's not to every polynomial satisfying the pentagon, I do a weird, complicated thing and pull out some other thing satisfying double shuffle. No, it's the same ones. And this is still really, really, really mysterious, at least why they're equal. However, the theorem that you saw 2 weeks ago by Prof did show one direction of the believed isomorphism. As far as we've ever calculated, they are isomorphic. It showed one direction of these believed isomorphism using polylogarithms. In a sense, it's related to what I said here. Polylogarithms are objects connected to multi-zeta values. They're actually functions. Its values are multi-zeta values that satisfy some associated-like things and pentagon-like things. And so they form a connection between the two sides. Okay? Now, to go the other way, you'd have to prove that the double shuffle defining relations imply the pentagon. And easier, you'd think, would be maybe to prove that the double shuffle defining relation define just relation 1, which already we know follows from the pentagon. Well, but it's impossible. No one has been able to do it. It is really more difficult than you would think. All we're saying is phi of xy times phi of yx equals 1. How hard can that be? Well, if you're given the Stuffle relation, it has nothing to do with phi of xy times phi of yx. It just doesn't, it hasn't been proved yet by anyone, and I mean, God knows that many people have tried. So,
This is the map.
this is this middle map here. It's just f of xy maps to f of x minus y. That's all it is. So that's the simplest one.
In the S3 and S3 tilde over there, is there not a minus sign?
I don't think
And
she said.
Well, I mean, it does, these are only, I mean, it's only defined up to scalar multiple anyway. This is an isomorphism from one to the other, but I can take whatever I want to be the generating. I don't have to take the image. Okay, so that gives the sketch of the first injection up there. You can see that all of these things is very recent work, all these connections.
Can I just ask about the first map? I mean, these three guys on the right, they live in the 3D algebra in two guys. But the
No, but yes, that's true, but wait. They live in there. You have to see them all. The right way to see it is in there. If you do that, and I told you, I know this is the hard part, that F acts on the FX. So this is the right way to compare them.
But F acts, but then you're saying that F lives inside GRT. So how do you embed the F inside GRT?
F, it's some derivations of the of xy, and GRT, it's some derivations of F of the of xy. This is the right way to think about it.
Well, okay.
Because that's just about as explicit as we can get. The fact is, I cannot tell you where S3 of F, some generator, goes. I can conjecturally tell you, but I cannot actually.
But it is known that F embeds inside GRT.
It is known. So I'm getting there. But before I get there, I wanted to talk about now. Okay, so there's one now which is not needed anymore, but it was done first. Well, it was done second, I guess. I don't know exactly what the order of all these results are. They're all very close. They're all in the last 2 or 3 years. And is this one, this injection here. So this was Alexeyev-Torossian. And essentially, we saw it yesterday in Damien's talks. He said, take f of xy in GRT, and you said A equals f of zx, z is nothing but minus x minus y, and B equals f of zy, and then you do the special automorphism, x comma A plus y comma B. Now what happens when you take an element in GRT and you do this? If you want to be inside KV, this had better be 0. Okay, so this is 0. This is 0 for all f in GRT. This was not proved by Alexeyev-Torossian. This was proved before. This was proved by Grothendieck. And it's hard. Although he writes it in about half a page lemma, when you try to understand the half a page lemma, it becomes a 5-page lemma. And it's really difficult. And now this I find very strange. So this is something that, were you going to ask a question?
Yeah. It seems to be just the hexagon relation.
You wish, and I wish, but it's not.
No.
So this is something that I found very striking yesterday. So I was listening to Damien, and he, at the very end of his talk, was saying a e to the x a minus 1, b e to the y b minus 1 is equal to this, if I'm not mistaken. And he proved that the hexagon on phi, so he did basically the same thing. From phi, he got an a that was, I'm not sure if I'm doing it right, because there might be an e, zx, zy. Do you have an e here, maybe? E something.
e to the y over 2.
But basically,
And it's phi x, z, and y, z.
you don't have to ask for the pentagon on phi, he said. You have to ask only for the hexagon, which is weaker than the pentagon, it's implied. And then, in a very obvious way, you rewrite the hexagon and you get this and it's done. And that does not work at all in the Lie algebra. It's wrong. It's actually not true. The relations 1 and 2 of GRT do not imply this thing. You have to have the pentagon to imply it, and a hard proof by Drinfeld. So that's something strikingly different between power series and the Lie algebra. It comes from the basic difficulty is that derivations are non-invertible. This is what's really disturbing in this case. It makes the usual argument not work. But then when you see that the usual argument doesn't work, it becomes all the more striking that the pentagon does make it work. Okay? So this was known for a long time, since 1991 by Drinfeld. And that shows that GRT satisfies the first defining relations of KV. And Alexeyev-Tarasyan showed the second, the div, the trace relation for elements of GRT with an algebraic calculation. Very nice Lie algebraic calculation using the pentagon and manipulating the letters. It's really pure algebra to prove the second one. So they proved this in their paper where they actually defined and studied this Lie algebra. And that paper, I don't know when they wrote it. It's come out in 2012, but I think it was written 2008 or 9. Okay?
So I may have one comment. So it's not so surprising that it works with the hexagon for the torsor and not with the Lie algebra. It's just because if you remove the pentagon equation on both sides and you just keep the hexagon, you do no longer have the fact that you have a torsor with a Lie algebra acting on it. So there's no reason for when you remove the pentagon and just get the hexagon on both sides that you have still a very nice picture saying that
things happen the same way.
Yeah.
That seems to be. And yet when you put the okay, so what you're saying is why the pentagon seems to work the same on both sides is because it's.
Well, because basically you can remove the hexagon and everything still works perfectly fine. But if you remove the pentagon, it just destroys everything. So.
Yeah. Although removing the pentagon has very, very good, rich geometric meaning, and you can certainly remove the pentagon from the Lie algebra, and that has a rich geometric meaning too. But they don't want to be compared anymore.
It's not. It's still even here. It's not here that it's still the Lie algebra actually.
Yes, of course, with just 1 and 2.
Is it still?
It's maybe not clear. I mean, it's a lemma, but it's also a lemma that GT with just 1 and 2 is a group. I mean, you have to prove it. You have to do a little work to prove it. Yeah, it's still in the algebra, and you can prove it's different from the one with 1, 2, and 3. It's actually bigger, so you know they're not equal. The 3 implies 1 and 2, but 1 and 2 do not imply 3, which is actually a legitimate question. Okay, so then okay. Now let's talk about this one. So because of this and this together, that sort of recovered the injection by Alexeyev-Tarasyan. This one, it's proved by pure algebraic manipulation. So it's due to a bunch of really pretty symmetry properties on elements of the double shuffle Lie algebra, which I'll probably start proving next when I've gone over the outline. Maybe that's what I'll start with. Okay. This is remarkable definition, I think. They're all remarkable definitions. Okay, for the time being, my favorite one is this one because I believe it's somehow the most economical, if the least redundant. This is a linear system, right? It's all a stuff of relations. The linear system is hugely redundant. And this one seems not to be. I have a feeling that it's possible that this is like the right expression of double shuffle, the economical one where you got rid of a lot of extra stuff. I can't prove the converse yet. In fact, I can prove that elements of double shuffle satisfy the two defining relations. Speaking, I'll get to more detail soon. Roughly speaking, by reformulating the definition of this, reformulating until I make them into nice symmetric properties of Lie polynomials, and then showing that these have those nice symmetric properties. And I just want to say two things. Two remarks. So the first remark is, if F is in double shuffle, then you set A equals f of xy, zx, just like I did over there for GRT, like Alexeyev-Tarasyan did. But B is equal to a certain function that I get from F, which I'll show you later. And then I get XA plus BY. I'll do this in more detail. I do get the first relation, the defined relation of KB, but I don't know at all whether this B is what I would like it to be. I don't even know whether, okay, I just don't know. It's true for GRT, and I cannot prove this for double shuffle, even though in every example it's always true. It's a bit like trying to prove relation 1. Looks simple, can't do it. And for general torsion, I don't know if you conjecture, but in any case, he asked whether you always have theta of A equals Z. Theta, not phi. Theta, where theta is just the thing exchanging X and Y. He wondered about this. In every example that you can calculate on your computer, it's always the case. And in the GRT situation, Z is fixed by theta, and it's true. So these are just switches of each other by switching X and Y. Related to this relation 1. But we don't know. We don't know. So even such a simple symmetry thing which would help to bring these groups closer to each other seems to be quite difficult. And the second thing that I have to say that's important.
Yes, can you, because we have the computer just in front of us, we don't see the board.
But if I put it up, you'll have the screen in front of it.
That's okay.
Should I put it up very slowly?
Is it okay?
You could move this screen.
Oh no, if I move that screen, the slide will go away. No?
Move it. Move the computer now.
But I want that.
Go to the other screen.
Put the computer on the table.
The computer, the screen is not moving.
Oh my God, really?
This move is not this, wow.
Modern day electronics. Okay.
I bent down and changed the page.
They gave me a memory stick before to put my file on the computer. And I said, I don't know how to use it. I got such nice patronizing smiles. Okay. Actually, I do know how to use a memory stick. I just don't know how to stick it in the computer in my office. I usually do know. I don't have that. But, okay. Okay, I have to say something really important before I move on. And the really important thing I have to say is, I have to talk about the work of Jean Ecard. So, I think Jean Ecard is somebody who's quite well known and has a reputation in France, quite a reputation, but he's probably completely unknown everywhere else because he never publishes anything, or very rarely. And his work is extremely hard to understand. And he has developed a whole language, which is very like a foreign language. Very nice, very, very beautiful. And he has done lots of work on double shuffle, which never in his life would he call double shuffle. It's a whole different word for it. But he's done a lot of work on this and multi-zeta values in general. Really, a lot of work. So I want to say that his work has some problems because you can't understand a lot of it. And he often doesn't write them down. And basically, he announces big results, and it's not easy to see whether he's really proved them or not. However, I mind his work a great length. And I found really very beautiful things. I mean, there's no doubt about it that he's a wonderful vision, a wonderful way of expressing things, and some results that are really good and really helpful. And his language is incredibly well adapted so that things that are complicated can sometimes be really simple, the way he presents them. And after doing the work of rephrasing the defining properties of this into nice little symmetry properties of Lie elements, then came the problem of showing that these had those symmetry properties. And for this, I was mining the work of Ecard. So one of them is something that both of them are things that he said, and I could not understand or find proofs in his papers. And one of them he actually wrote me a proof, which was very short but sounded like Martian. So I had to translate it. And it became long, which is a bit sad. But so I understand one of them, we rewrote it in a paper with one of my students completely and published that.
Maybe you can say it's a second condition in case.
I'm going to come back to it. I'm going to actually give much more detail on the proof of this. I just want to make a remark now. The other one is something which is the fundamental principle of all his work. It underlies everything he says, amazingly beautiful identity. And I translated it, and it turned out to be this property, exactly the one that was needed. But I haven't been able to parlay his thing into normal algebraic language. I can translate his relation into what we need. It's any kind of proof of his relation, or how he proves it, or how he does it. That's. I believe it 100%. I think he's really. I'll tell you what. This is what I think of Icahn. When he says things that he's found in his own language, in his own way, it's incredibly right. Mm-hmm. When he, which is very rare, tries to prove something that somebody else asked, it can be quite wrong, because he doesn't really care. Okay. Anyway, so I'm going to get back to the proof of that. That will be my last half hour, pretty much. There's more details on the proof of this. But before that, finishing my outline. Okay, so what about this? This injection of the free one into GRT. Okay, this, I can't explain anything about this without introducing a majorly different concept. And, okay, the whole afternoon, a large part of the afternoon will be devoted to multiple zeta values. And motivic multiple zeta values, and even saying very little, there's still need time. But basically, what he based his proof on work by Goncharov. Goncharov, he defined some mixtape motives, one associated to each multiple zeta value. So he just calls them motivic multiple zeta values, with an N. And they are actually mixtape motives, which means, again, that they are vector spaces with an action of that group, and they come from the geometry of genus zero moduli spaces, or the geometry of P1 minus 2 points. This is how he creates them, with iterated integrals. Something I'm not going to get into these details at all, because there's going to be a whole course next month. But in any case, he defined mixtape motive attached to each one that form a subcategory. And because they form a subcategory, you have a surjection from the fundamental group of GMTM to the fundamental group of this category. I'm going in the right direction. And so a surjection from the Lie. This one we saw is just S. And this, I'll call it motivic double shuffle. Let me just make a little diagram here. Here you have symbols which look like zetas, but they're just formal zetas. They're formal symbols subject only to double shuffle. This is double shuffle, nothing else. And here in the dual, you have the double shuffle. This forms an algebra. Here you have the Lie algebra, and what happens when you dualize? So these are duals. This is duality. This is a Hopf algebra because it's a universal enveloping algebra. So this dual, this is also a Hopf algebra. Here you have a Lie algebra inside, and the dual, you have to quotient by products. This typical diagram, quotient by products and by constants. And then these are dual. And this is a Lie co-algebra. And what Goncharov did is he defined these motivic multiple zetas, and they form a Hopf algebra also. And he proved in a very difficult way, that these satisfy the double shuffle. So, Ismail gave a much more straightforward and geometric proof of this using, and I really like this, using the geometry of genus zero moduli spaces. So we have a surjection here just because they do satisfy double shuffle, and this is formal things that satisfy only double shuffle. So I have a surjection here. And what that means, and then you can go down mod products. Let me give a name to this. NFZ. These are new formal zetas. When you go mod products, You drop everything that's old in the sense of coming from products of other ones, and you keep. What you do when you go mod products is you're giving yourself ring generators, right? Ring generators of your ring. And here you do the same thing. And here you have a surjection. Okay? You just drop products and keep only ring generators. And Goncharov also proved that this is a Hopf algebra. MZ. This one you know it's a Hopf algebra. Because this is you know this is a Lie algebra, but it has Sinus theorem, that's hard. But given that, this is a Hopf algebra, so that's a Hopf algebra, so there's a coproduct. Goncharov proved that this is a Hopf algebra, and it's the same coproduct that goes down. So here you have a surjection, and therefore here you have an injection of the dual. Okay? Now, in this diagram that I've made, I can replace ds by GRT. Let me take a color. Because if you can define formal zetas that satisfy only double shuffle, because you know the real zetas do that, you can just as well define a different set of formal zetas that satisfy only associated relations, because you know the real zetas do that. So you can replace everything here. You can make both diagrams. And again, Goncharov proved that the motivic zetas also satisfy the associated relations. So these, it injects into double shuffle, and it also injects into GRT, and this one injects into there. Okay, so it follows from Goncharov that this MMZ duo injects into Gert, which injects into double shuffle. Okay? And what Francis Brown proved is that this surjection, well, okay, now I could call it NMZ. This surjection is an isomorphism. So this is Brown's theorem. The map here, it comes from the fact that this is a subcategory, and what he proved is that it's the whole category. Essentially, if the fundamental Lie groups are isomorphic, the categories are the same. This surjection, it's an isomorphism. The categories are the same. So what he proved is that these are the same category. Well, not isomorphic. They're equal. This is inside, and it fills the whole thing up. Which is to say that all mixed tape motives are essentially these motivic multiple zeta values, or come from them. Okay? So his theorem can be interpreted on many levels. The equality of categories of mixed tape motives, of fundamental groups. But if you just look on the Leave level, and they're all equivalent. So there's a very simple statement. On the Lie algebra level, the statement is simple. And yet it's equivalent to all these other statements. It's just that this is isomorphic to the free Lie algebra. And he did this by a dimension count. So he actually calculated the dimensions of these and so they were equal to the dimensions of those. Okay? And the thing about MZ, these motivic multizetas, the thing about them is, in one way they're nicer than formal zetas. Because we know now, thanks to this theorem, we know the dimensions, we know what the algebra is, we know now that it's the free Hopf algebra on one generator in each odd rank. We know that it's MZ duo is the universal and revolving algebra of this free Lie algebra with one generator in each odd rank. The Lie algebras all live on this side of the diagram. And here's the dual side. Okay? We know the dimensions, we know exactly the structure. So in that sense, motivic multizeta values are nicer because, well, we know the structure. But where they're less nice is that we don't know the algebraic relations satisfied by motivic multizeta values. We know they satisfy double shuffle. We know they satisfy associated relations, but they may satisfy others we don't know, because this surjection here, of course, to say that we think all these Lie algebras are isomorphic, it's like, then we believe that this is isomorphic too, right? But we don't know. So at least if I take formal zetas, I can say, I know they satisfy double shuffle and that's it, or they satisfy associated relations and that's it. Whereas with the motivic multizetas, we don't know. So that's one of the reasons why these isomorphisms would be nice, the ones in the main conjecture. Because, for instance, we could say, passing from purely formal multizetas that satisfy only double shuffle to motives is an isomorphism. So we don't need to work with motivic multizetas, which are heavy to define and so forth. we can just say everything we're going to say directly on. Basically, to prove this isomorphism would remove the need for geometry. Not that we don't like geometry, but you wouldn't have to resort to geometry to understand them, because a purely combinatorial definition would define them completely.
But on the other hand, sometimes geometry helps us to prove algebraic facts.
Well,
So
that's what's happening
removing
here.
all the geometries might not be. The first step seems, oh, it's okay, we have purely algebraic things and combinatorics, and then when we put our hands into the combinatorics, how do I prove that? Which one?
Everything that's happening in this situation is that not everything. No, not everything. Some of the proofs are purely algebraic, but some of the proofs in this situation are really, really appealing to the geometric content of multiple zeta values. I'm not saying it would be a good thing to stop doing that and do only combinatorics forever, but I think it's important to know how much the problems you're looking at are purely combinatoric. And personally, I would really like to know, to be able to say that the only relations between motivic multi-zeta values are double shuffle or whatever, rather than there are some mysterious relations that nobody knows and we don't know what they are. Okay, so this is the main ingredient used in the proof of Brown's theorem. It's actually not an ingredient; it's a whole theory. It's a whole theory of motivic multi-zeta values. And given that whole theory and this map, he proved the isomorphism of the two. And since we saw that we had this injection here, well, that makes now that F injects it. Okay? Okay, so now, I guess the introduction is going to take up the whole talk.
Can I just ask a quick question? So, reading Cassel or Schiffman, I think, of book, the Turing-Phelps paper, he already mentions that conjecture, that F, the 3D algebra on one odd generator is isomorphic to GRT. That's a long conjecture.
Long-standing
Yeah, and in the first new step says Francis' result, that relating the 3D algebra on odd generators to these motivic things, he was able to prove the embedding. The injection.
Well, there's always been a map. Okay, it's really, okay.
Yeah.
So, a map from F to GRT, many maps, not a canonical map, many maps, have been around for a long time.
Okay.
By a reasoning which, maybe Damien didn't talk about this. Okay. Okay, I'm going to give a cheap reasoning. It costs less than the good reasoning. Let me give you something really simple. Take phi kz, but take bar, so which just means reduce the coefficients, multi-zeta values, mod products. Okay? And then we fall into the Lie algebra. If you do that, then the image is the same as the image of log, because the log is all products. So you end up in the Lie algebra. So I'm going to just write this, but it's a Lie. It's in GER. It's in GRT. You know that it's in GRT because it satisfies the associated relations. But with coefficients that are in, well, they're zeta values. They're in R. Now, take a basis for multiple zeta values. They're real numbers. They form a vector space over Q. In each given weight, the weight of a zeta value is A1 plus AR. So just write down all the zeta values to a finite number of weight n. Real numbers. They form a vector space over Q. Take a basis. I'm talking theoretically. This is not easy to do in practice. You have to use some logiciel. But in theory, just take a basis and rewrite this in terms of that basis. So you gather everything. So you have a zeta 3, say, and then some polynomial, and you have a zeta 5, and some polynomial, and then you have a zeta 7. You're going to have some double zetas, 3, 5, and so on. So you just take the zetas you need to form a basis. And these polynomials here, they're all defined over Q, all these polynomials. And they all lie in GRT, over Q. So here, by this little method, which is totally uncanonical, you get a bunch of elements in GRT, and for each single odd zeta, you get a polynomial. let me call it Pn in GRT by doing this. And this is completely uncanonical since I've just taken a basis, but let me suppose my basis includes a zeta n for each odd n. And this Pn has the property that the coefficient of x to the n minus 1y is non-zero. Because it appears in the original associator, zeta of n is zeta of the word xn minus 1y, and it comes in front of that word. So the term xn minus 1y, it appears right here with a non-zero coefficient. So you know that goes into Pn and has a non-zero coefficient. So for every odd n greater than or equal to 3, you have an element here, which I can call Pn. It's for the odd n's greater than or equal to 3. And you send your Sn to that. And there's better ways to do it. So Grothendieck gives a more canonical, nicer way to actually choose these. Using the torso reasoning. You have phi kz of xy, and you have phi kz of minus x minus y, which is a different associator. It's a different Grothendieck associator. And since Grothendieck associators are a torso under x with GRT, you have an x of some element in GRT, which does this. And this one, you can prove it has no even part, and you take the odd part in each different way for the Pn, so it's just a different method. But in any case, every time you choose an element in GRT of odd weight and with this coefficient here, with this coefficient non-zero, you get such a map from F in there. And it was conjectured a long time ago that this was an isomorphism and proved in all small ways, calculated that you don't have anything more in all small ways. So what Francis added to this is I'm going to say the injectivity because I don't think from Francis' result that you can get that this is injective for any choice of Pn's, not at all. What he says is there is a choice of Pn's. There is a choice of Pn's which will work. This is canonical. There isn't any choice for the image of F. You have to choose your Pn's inside the image of F, and the trouble is nobody knows how to do that because we don't know what the image of F is because we cannot calculate this thing. And the reason we cannot calculate this thing is because we don't know what the kernel here is. It's the same as what I was saying before. There may be other algebraic relations satisfied by motivic multizetas. Of course, we don't think there are, but there might be, and we don't know what they are. So we can't say what this injection is, so we can't say what this injection is, so we can't say what the image is. You give me any element of GRT. I have only one argument to tell you whether it's motivic or not. Motivic means coming from the F, which is dimension. If the dimension of the weight n part of GRT is equal to the dimension of Fn, then I'm happy because they're all going to come from there, right? Now this is always true. If you want to calculate, it's always true. So I can happily tell you that everything in GRT that we can calculate is motivic, but that doesn't really help for theoretically speaking. Okay, so then I guess I'm going to finish. Now I've lost the computer. But this was the last slide, so that's fine. I'm just going to end up with this. This is the last. I guess the introduction is what I said. Okay. So what I'll do this afternoon is sketch the proof of ds goes into kv, just little bits of it, but to give the flavor, and sketch the proof of talk about the connections with multizetas, formal and motive. Okay, I want to talk about this last now. This last thing I find very difficult to understand. I really have trouble grasping how this works. Even though I've persuaded myself about this isomorphism many times, every time I try and figure it out again, I don't know anymore. So I hope I'll get some help. It seems that this isomorphism, the one of DIL with F. Oh, I should have written F tensor QL. By the way, I should say that when Deline and Hara defined DIL from L, the first question they asked was, is this motivic? And by that, they mean, specifically, does L have anything to do with it? Or is there some Q algebra, which now there is, it turns out to be F, such that when you tensor it with L, you get all the DILs? So the answer is that yes, it's motivic, and in fact, this is the motivic fundamental Lie algebra of mixed neighborhoods. Okay? So the proof I'm about to try to give you answers that question, and it seems to me that this proof should be a reasonably easy corollary of everything I've said up to now, but I have a difficulty remembering how this works. There's something in it that I don't really grasp, so let's... First of all, Ihara showed DIL injects into GRT tensor QL, and GRT is their star of Lie P5. Now let me just remind you that we saw something exactly like this in the group situation, where the profinite Grothendieck-Teichmüller group was out star S5, this is S5, of the fundamental group of the Gina 0 moduli space with 5 mark points. This, it meant preserving inertia, conjugating inertia elements, and here it means that each generator xij maps to a bracket of xij with something in the algebra. So this star here means that you have a derivation of this type on the xij generators. And it commutes with the action of S5, just permuting the indices up to inners, and that we saw here. Okay, so this, which was proved by Ihara long before the group situation, is an analog of the profinite group result that we already saw. And this comes from the fact that GQ also acts on this. We saw that also. This is just a fundamental group of something defined over Q, a Q variety essentially. And so the programmatic completion of the fundamental group has this Galois action. And it always preserves inertia. Galois always preserves inertia, and S5 is just defined over Q, so Galois commutes with it. And this, it's not just an analogy. This reasoning descends directly to this. So far, I have that. Now, I just showed you also that we have motivic multizetas inject into here, the dual. Motivic multizetas are the quotient of this mod product, and the dual of them injects into here. And that Francis shows this is free. So far, I have no problem with this proof. The place where I always... Can you help me? It's a proof that the images aren't the same. What you have to show is you have to show the images are the same. If you prove the images are the same, you're done. If you prove that plus Hein Matsumoto had shown a surjection here. They showed, Hein Matsumoto, they showed that this was generated by one generator in each odd rank, which is completely understood as an element that you can explicitly get from the absolute Galois group by acting on a certain number field. It's completely done with theoretic, the generators of this. Okay, so what you want to prove is that there's no kernel. But this diagram seems to prove that there's no kernel, because if this had a kernel, then since these are equal, this would have a kernel, but it's injected. Only I haven't shown you the diagram commutes. So I've given you everything in the proof except this one fact. You have to show this diagram commutes in order to prove the isomorphism. This is, we know it's a surjection. We need to show it doesn't have a kernel. The technique to show it doesn't have a kernel is to say, well, it goes here, and that is an injection by the whole theory of motivic multizeta values. So how do you prove that this diagram commutes? You have to show that they have the same images. How do you show that? I've talked about this with you many times.
No, I think you need an arrow in the other direction from DIL to motivic zetas, which is natural, which is the fact that you have this state realization.
Can you give us like a 2-minute lecture, maybe? Maybe I should say this is just not written down anywhere. Okay, maybe I should say that the reason why I'm swimming is because no one has written this
No,
down.
no, no, I don't think it's well done, reasonably well done in Yves André's book, frankly. Yves André really explains why you have an arrow in the other direction. I mean, okay, when it's written this way, it's a little difficult to recognize, but you have an arrow from DIL to this, which is natural and makes the thing commute, so this is basically the Tate realization.
Oh well, if you have, if you have two arrows, you don't need the rest of the
You have gamma
diagram.
modules, and this is the arrow it gives. But, well, okay.
Maybe we could
Let's
talk
say I
over
would
lunch and
refer
give a
to-
better 5-minute
I mean,
discussion.
I would refer to I mean, you can explain
should
it,
write
but
this
also
down,
it's well explained by Eve, I think.
Okay, let's look it up over lunch and start 5 minutes
No,
this afternoon.
How the DIL is far away from the L-adic realization of the pro-unipotent completion of pi1 minus 3 points? Do you have the fundamental group of pi1 minus 3 points?
No!
And
DI and all of the other algebras I'm looking at are generated by one thing in each odd weight. What, S3, S5, S7, and so on, whereas the one you're saying is just generated by X and Y. The one, this, X, all of them, all of the F and the GRT and the DS and the KB, all of them lie in this. Okay, now we can understand this better. Because there's an injection in here, and this does lie in the there in an explicit way. So, but this one is not explicit. So you have to just believe that there's a canonical map here. But at least once you know that, okay, there is an action, we can't calculate it, but you know how it is. I think it would be good if I stop here. I'm going to stop, and maybe there's so much more to say that it's make a traffic jam in my
You have
brain.
2 hours.
Okay,
and-
better stop. Yeah, the best thing is just not to say any of it. Now it will be settled. Yeah, let me try and figure out that final point over lunch and start with that. But that's just a tiny argument. It should be a 5-minute remark. But I cannot figure this out completely straight in my head. Somebody should write it down for you. Okay, we'll go look in Yves André and see if it's good.
Thank you very much.
Okay,